Hello everyone, myself Aryan Gupta, and today we're going to study enhancement N-type MOSFET. So basically there are two types of MOSFETs, enhancement type and depletion type. So the only difference that this MOSFET has from the depletion type is that it does not contain a particular dedicated channel. Okay, so basically we will first study the construction and then we'll study the operations, different modes of operations, and then we'll study the characteristics of N-channel MOSFET. ठीक. So basically, here's the construction. We have a p-type substrate, which is moderately doped, and then there are two n plus regions, which are heavily doped because they contains the carriers, basically the n-type carriers, which is electrons. And here is this substrate and this source is internally connected most of the times, or maybe this substrate is grounded. And here's the source, here's the drain, and here's the gate. And the gate terminal is the main, the driving force, the main thing that controls the operation of a MOSFET. So the gate is a very important thing. And here we have some metallic contacts here, and there's a layer of silicon dioxide, which basically separates the gate from the P-type substrate. That is the main function of silicon dioxide. And the drain here is connected to the N plus region. So this was the construction, and we can assume it like this, that there are two PN diodes which are connected in series like this, because here is P, here is N, so NPN. And now we'll see the operation, like how does this thing operates. We'll study that. First thing, we have to see about two voltages, which is VGS and VDS, which is voltage from gate to source and voltage from drain to source. Okay, so the first thing is when both the voltages are zero, no current flows. Okay, there is no flow of current because as there are no charge carriers. Okay, this thing contains electrons, and here's the holes as the majority carriers. So without any voltage given, like VGS is zero and VDS is zero, there would be no current flow. So there's the I equal to zero, no channel formed because no channel is formed. Okay, no electron channel is formed. So how can the current flow? Second thing, when we give a little bit of positive voltage to VGS and VDS is still kept at zero, then little bit electrons start accumulating here because of obviously if you give the positive voltage here, some minority carriers from P-type substrate starts to gather here and they make a layer. For example, like this. In this image, you can see a little bit of channel formation happens because of the positive gate voltage, and obviously all the holes that are in the P-type are drifted downwards in the downwards direction. They are repelled due to the positive charges. Now you can see, like, you can assume a sort of a channel forms between the N plus regions, like in depletion type MOSFET, and when we move ahead, when we give more positive VGS voltage, there comes a point which is called VTH or VT, threshold voltage. This is the minimum amount of voltage that is required to flow current. All right. So when we give a little bit amount of VGS voltage, a depletion layer was formed, and when we increase the voltage to VTH, like the minimum voltage, then an inversion layer was formed of the electrons, like this. You can see the electrons are collected here, and the holes are collected here. So we can see that the operation of the MOSFET is enhanced by giving the positive voltage. That's why it is called enhancement type MOSFET. That is the reason for his name. And now the electrons are accumulated here in the channel. We can easily give the VDS voltage, which is the drain to source voltage. Okay, and because of that, this is the electron flow, and this would be the current flow in the opposite direction. And the current is ID. This is what ID, the drain current. And the drain current would flow like between the drain and source. IV would always be zero. Okay, there would be no current here. This layer, there would be no current. And the substrate is eternally connected to the source. You can see, and then grounded with respect to. Now we move ahead. We gave the VDS, we gave the VGS, and the MOSFET starts to operate. The current starts to flow, the ID starts to flow, and there comes a limit. Obviously, if you will keep on increasing the VDS, obviously there would be a limit. So if VGS is kept constant, like suppose you choose key, let's give 2 volt VDS, fix threshold voltage is suppose 1.5 volt, and you give VGS equal to 2 volt fixed. And now you keep increase the VDS. Obviously, the current ID would increase, but to a certain point, and after that it saturates. So this thing is called the saturation region. This thing is called the linear region, and before that was called the cutoff. We'll see that in the graph too. So obviously, when you increase the VDS voltage, the current comes and saturates. And if you see VDG, that is voltage from drain to ground. So it is VDS minus VGS. This is kept constant. This keeps on increasing. So this would increase, and if this would increase, the gate voltage would decrease. Hence, effective bit here would decrease. The effective channel bit would decrease. And hence, a pinch off occurs. We can see a pinch off in the channel occurs. This is the beginning of the pinch off, the saturation region. And VD set, that is the maximum amount of voltage above which the current saturates, is given by VGS minus VH. By this. This was the whole operation, and the current saturates after this. And we're assuming here the ideal MOSFET, right? We're not considering any channel modulation or any other effects, body effects. We're not considering that for now. Now we'll move to the characteristics. So obviously we need to study two characteristics. There's the drain characteristics, drain, which is ID versus VDS, and the transfer characteristics, which is ID versus VGS. And obviously we can say that this is a voltage control device because the voltage VGS here is the main controller for the current. So this is a voltage control device. MOSFET is a voltage control device. So this is the characteristics. We can simply see that we need a particular amount of threshold voltage to make the current flow. And if we keep on increasing that, obviously the current will increase, and current also increases with the VDS. So this region is the linear region. It's because dV by di here is given by the distance, and this is the linear region. This is the saturation region because the current obviously saturates. Like for example, if we put VGS equal to 6 volt, current would start increasing and then saturate because of VDS. And beyond that, that's called the cutoff region where no current flows. And we have some equations also. You can see that the current equation, the saturation is given by this, the linear region is given by this, and then the cutoff we know it is 0. And obviously, when the channel condition effect is considered, lambda is considered here, 1 plus lambda VDS factor comes, but we're not considering that for now. So this is the equation for the current in all three regions. And last, the transfer characteristics, which is between ID and VGS. Obviously, ID is in milliamps. Between VGS and ID, you can plot that easily. That we need a minimum amount of voltage VP for the current flow, and then decreases like this. So this was the MOSFET, natural MOSFET enhancement type, and this was all its construction, operation, and the characteristics. Thank you.